equivariant principal bundles on toric varieties, part 1. So, and the part 2 will be tomorrow by ICTS.
Well, thank you very much for the introduction, and thanks to the organizers for the invitation. It's been a great experience. So our work is joined with Indranil Bishwas and Arijit De, and Arijit will speak tomorrow on the second part. So we'll try to classify equivariant principal bundles. So on toric varieties, so toric varieties are algebraic varieties. They're compactification of a complex torus. And by equivariant principal bundles, I mean, so the torus will act on the toric variety, and I have bundles, principal bundles on which the torus acts, the action can be lifted, and we try to classify such bundles. Okay, so the first problem we encounter is a local classification. So what is the classification over an affine variety? Okay, so for that part, I'll try to give you some general results, and I'll try to tell you what was kind of known, and so then we'll give kind of a more general result, and then we'll apply it to the case of toric varieties. So let's take X to be an algebraic variety. And some of the results will make sense by other people, will make sense over an algebraically closed field, but our work is over the field of complex numbers. And well, the structure group of my bundles, G will be a linear algebraic group. Okay. In Arijit's talk tomorrow, G will be reductive, but today it's more general. Okay. And we'll consider principal bundles over X. So principal bundles, a principal G bundle, algebraic. Okay. And now, so I'll mention some local classification results that were known previously. So if X is the affine space, then EG is trivial if G is reductive. That's a theorem of Raghunathan from the mid-70s. Now, if okay. Now, for singular varieties, affine varieties, not much is expected. It's not really expected that you would have a trivialization. But in a special case, so if X is affine toric variety, and G is GLN, sorry? Okay, so EG is a principal G bundle. This, sorry? So what I mean is you have a algebraic variety, and you have this map, which is a fibration, and each fiber is a copy of G, and G acts. Yeah, it's so this is yeah, general. And G is GL. Okay, GL, and so X. Sorry. So G is some GLV, then again EG is trivial. So this is a result of Gubeladze from the late 80s, I think. Okay. So now, so this is just, the field is K and dimension is N. No, not necessarily, no. No equivariance is necessary there. Sorry? Yeah. So toric variety. I'm not sure, K is very special there. So K is, I think, probably, or I'm not sure if it's any algebraically closed, but could be even just complex numbers in Golan's result. So now, so equivariant. So equivariant principal bundles. So this is so here I have a group gamma acting on the base, and well, for our purposes, I'll take gamma to be reductive. I'll only talk about reductive groups. And again, you have a principal G bundle, and you have a lift of the gamma action on the principal bundle. And so the gamma and G actions commute. So this is definition of an equivariant, gamma equivariant principal G bundle. Okay, so in this case, again, there are few, very few results, local classification results. So I'll try to tell you what was known. So this is yeah. So this is resolved by Masuda, Mosher, and Petri from mid-90s, and so there is okay. So now, so I should first define what is what I mean by what I mean by a trivialization in the equivariant sense. Okay, so. So we say that, let me give this a symbol. Let's call this entire thing xi. So say that xi has a gamma equivariant trivialization So if there exists an isomorphism phi from EG to X cross G over rho, where so this is a gamma equivariant isomorphism of principal bundles. So basically, it's a G equivariant isomorphism of fiber bundle, and also additionally, it's gamma equivariant. And this rho is a homomorphism from gamma to G. And on X, you have, on this side, you have the diagonal action. So on X cross G, you have diagonal action of gamma given by such a homomorphism. Okay, so, not only is this bundle trivial, but also the action has been trivialized. It's given by one. So, essentially, if you have, let's say, if it's given by one homomorphism, and if you have a gamma fixed point, the action is fixed by the action of gamma on the fiber over that fixed point, in case there exists a fixed point. So, okay, so now I can describe this local classification results. And there, you see, they're very weak, like very special kinds of G and gamma. So one result was by Masuda, Mosher, and Petri. So they had G equal to GL and C. And gamma is abelian, and X is a gamma module. So in that very special case, they had a trivialization result, which was actually some nice paper. Then, okay, now, when X is toric variety, so X is affine toric variety, and gamma is actually the torus, the torus that acts on the toric variety, and G is again GL and C. There's a local trivialization result by Kaneyama and independently by Kliachko. And sorry, complex torus, yeah. Yeah, so yeah. So sister, well, maybe it's better to say this is R rank, and this is sister to the dimension of the toric variety. Okay, and okay. Arijit and I, when we first tried to study this, we had a result when, yeah, so X is again affine toric, and gamma is torus, and G this time we could go to some subgroups of, so from the vector bundle case, we could go to some, other principal bundles. We could do it for G is a abelian, so it's a linear algebraic group which is abelian. Sorry, yeah. Okay, so all right. So now I guess. So there is here. Yeah, so there is such a local trivialization. Okay, so Can you? Case 2. Torus. Yeah. Yeah, so it's basically a torus acting on. Yeah, so torus, of course, what do you mean by diagonal? But yeah, I mean, up to some transformation, yeah. Up to some, transformation is diagonal. So,
can you explain that again? It seems to be getting weaker as it moves down the board.
So this kind of, this is a hard problem. Actually, you can do things for vector bundles, but to do a reduction, equivariant reduction of structure group, that's difficult. So if you have subgroups of GLN, that actually becomes harder. So now we have a very, much more general result, which I can state here. And so this is our also, interestingly, there are counterexamples. So even if you take, so I should mention this, that there, in general, you don't expect such, equivariant trivialization. So there are counterexamples by Jerry Shores, also I think from sometime in the 90s. What it says is these counterexamples basically gamma reductive even, but it acts on X with the quotient having a dimension 1. So if X mod gamma has a dimension 1, in that case, he produced counterexamples to even G with GLN, I believe. So, okay. So now, here's our main result. Okay. So, X is a affine variety over C with at most factorial singularities. So what we mean is that the local general is general. So actually, yeah, so with at most, so by factorial singularities, what we mean is that local rings are not unique factorization domains, but factorization domains, so that every function will have a product decomposition into irreducible factors and units, but not necessarily unique. That is necessary for toric case. In toric case, you don't have unique factorization. So that's the type of singularities we can have, but it covers the toric varieties. Gamma is a reductive, as I said earlier, group acting on X with a dense orbit. So you see, this then means that the quotient of x by gamma is zero-dimensional. So we avoid. So this assumption is like our key assumption. And then there's more assumptions on the action. We assume that x is gamma equivariantly. So maybe we can consider the underlying real subgroup. So equivariantly contractible in real topology. Okay, so sorry? Okay, so there will be a gamma equivariant homotopy to a point so everything in the real topology. So, so then this will have, because of this contractibility, there will be, the point to which you contract is a gamma fixed point. So suppose over complex numbers. Yeah. So, well, no. It's just a Lie group over the reals. Sorry? The gamma is a complex manifold, so there's an underlying real manifold. So that's what I mean. Yeah, the real Lie group. Yeah. So, yeah. So suppose let x0 in X be a gamma fixed point. Because it's a closed point is fixed by gamma action. Okay. So now let e.g. X will be a gamma equivariant principal G bundle, algebraic. So here, then there exists a gamma equivariant trivialization in the algebraic sense. Then there exists a gamma equivariant isomorphism phi from EG to, well, actually, I would like to write it in the other way, from X cross rho to EG X naught, the fiber at X naught, so gamma equivariant isomorphism of algebraic principal bundles, G bundles. Okay, so what is rho? So rho, some homomorphism from gamma to G. Okay, and right. So now G has a, from the principal bundle, you have a natural G action. Yeah.
So does it follow from the assumptions earlier that there is a gamma fixed point, or
Yeah, by the contractibility. By the contractibility, there is a gamma exponent. Now, yeah, so, okay, so, yeah. So there's a natural, given G action on the fiber, and so you just compose that with rho to get the action of gamma on the fiber. So that's what I mean by this notation. So, and then you have the diagonal action of gamma on the base and the fiber, and this is supposed to be isomorphism, okay? So let me first tell you how we get the rho, and then so the explanation of rho. Okay. So just take a closed point in the fiber. So this fiber is fixed by gamma. Now then take gamma in gamma, and the rho depends on the choice of E, okay, but they're all conjugate to one another. So what I do is gamma times acting on E, because it remains in the fiber and the group G acts transitively on the fiber, you can write it as E times some element depending on gamma. So this element is in G. And then you can easily show that then rho is a homomorphism follows from the fact that the gamma action and the G action commute. So gamma and G actions commute implies that rho is a homomorphism. And all right, now if I change, so if I change, E to E dot some element H, say, and then I can write gamma of, okay. So gamma, commutes with the, let's write it G. So gamma commutes with G action, so that means this is like this. And then this means that you have E rho gamma G. And so I guess, this is kind of standard EG, and then you'd have. So anyway, so what I observe is that, if I were to change that reference point, I would actually get a different homomorphism. Okay, so next we come to the proof. The proof is actually simple. So, proof of theorem. This is a key step. So, that we had to do. The other steps are kind of, already available in the literature. So, So step one is it is enough to show existence of an analytic trivialization. So that means, the analytic trivialization will, under these assumptions, will imply existence of an algebraic trivialization. Okay? So, and this is how it works. So, so we fix an element of that fiber, okay? And we define, so assume we have analytic trivialization, also called phi, from X cross the fiber to EG. And so this is analytic isomorphism and gamma equivariant. Then you can define a section, right? So you can define a section, analytic section, sorry, S by S of X is a phi of X comma E. So from the product you go to the, using the trivialization. So, okay, I want to prove that this X has one, maybe I leave those conditions, has one nice property. And so I'll pick any gamma in gamma, and I do a calculation, gamma times Sx, so how it acts. And so this is gamma times phi of X comma E. And because phi is gamma equivariant, this becomes phi of gamma of Xc. And on the trivial bundle, you have this row. So you can write this action as phi of gamma x times e dot rho gamma. And now you can, because again, this rho gamma is part of the G action, and phi is again G equivariant. So what you can do is, this is phi of gamma x E rho gamma. So you see, it's a kind of very rigid thing, so you can do. Okay. And so what did we have here? This is, by definition, this is a section at gamma x times rho gamma. And from this, right, we can see, so this calculation implies that S at gamma x is just gamma acting on Sx and rho gamma inverse. Okay. So, yeah. Now you choose X to be a point in the, because we're saying gamma has a dense orbit in X, you choose a closed point in the dense orbit. Okay, so let X be a closed point in the dense gamma orbit of X. And all right, so then you get an, now what you notice is well known. So rho is a analytic group homomorphism of linear algebraic groups. It's well known then that rho is an algebraic group homomorphism. So we know rho is algebraic. The action of gamma is algebraic. So gamma action is also algebraic. And so over the dense orbit, we have an algebraic section. So this means S so this implies that S is an algebraic section over a dense orbit that admits a holomorphic extension because, okay, which admits a holomorphic extension, I should say analytic extension over X, and then with my assumptions about, so if you have some kind of, it's a rational map, and holomorphically you can cancel out if there is a, irreducibles factor which becomes 0 in the denominator, you can cancel that out holomorphically. And so you'll be able to cancel it out algebraically. And so then that means, this S is algebraic over X. And this condition that I have, well, anyway, so you have actually this condition, yeah. So having such a section is kind of, equivalent to having a equivariant trivialization. And such a section is often called semi-equivariant section with respect to the gamma action. Semi for this extra part, the rho part. So that's the theorem. And now if you look at it, so one kind of examples where you could apply it is you take X to be a linear representation space of gamma. You need a big group so that it acts with a dense orbit. And so that's one place where you could use it. The place then where we are going to use it is for toric varieties, affine toric varieties, and they will have such factorial singularities. I mean, all their singularities are of this type. Okay, so that's the local picture. So then, from here it is kind of easy to go to the global picture. So, but maybe I will tell you a little bit about the toric variety. So, it's made up of finitely many affine pieces, and finitely many torus stable affine pieces. So on each piece, I have the trivialization, and basically I just want to make sure that the transition maps are equivariant. and then it leads to a condition. So let us, I'll state the result only for complete, in other words, compact toric varieties. If you want to do it in general, we have done it, but things become a bit more complicated. So I'll avoid that. And so here is complete toric variety. Okay, so because Origit will use some of this fan description, I'll try to give you an idea. He won't have time, so quickly try to say what a fan of such a toric variety is, okay? So, you know, one of the quintessential examples is, say, projective space. You can even think of, say, P2. And, well, P2, there is a nice kind of, I know, the polytope picture for such projective toric varieties. And, well, this picture is very well known. The interior kind of corresponds to the open dense orbit is C star square. And each of these, so I'll put 3 vertices. The vertices are, you know, the points 1, 0, 0, 0, 1, 1, 0, 1, 0, etc. So let's say that this is in homogeneous coordinates 0, 0, 1, 0, 1, 0, and so on. And these are the divisors. Oh, these are the smaller torus orbits. Each is a copy of C star. And so if you take the closure, you get the torus invariant divisor, which is for CP1. Okay, so you have 3 of these special copies of CP1, and the torus in the middle, and everything is decomposes into orbits of C star squared. Okay. Now, if you have such a picture, each divisor, you can. So to each such a divisor, you can associate the stabilizer subgroup. Okay, so there is a, you know, from this C star squared, you actually quotient out by a copy of C star to obtain that. Or in other words, you can describe this torus action, C star square action on the entire, on this divisor. Sorry? It depends on the coordinates you write. Like, but now C star squared action on C star squared, this standard multiplication diagonal action. Okay, but when you go to this divisors, say, what you do is the thing is you have an isotropy you quotient out by a C star. And that's how you end up. That's the action on the divisor. Okay? It has a stabilizer. So you quotient out by different, you know, copies of 1 parameter subgroups C star. Okay, and okay. So now associate stabilizer isotropy 1 parameter subgroup. And 1 parameter subgroups, you see the characters are discrete. There's some lattice, Z2 here. And the dual lattice is the 1 parameter subgroups. So these 1 parameter subgroups, you can, you know, identify with elements. So suppose you say that this is the torus. Here you have the character group, which is, in this case, for C star squared, is isomorphic to Z2. And this isotropy 1 parameter subgroups, they, so there is a natural pairing, right, of functions with, you restrict functions on those subgroups. So that's a pairing. And from that pairing, there's elements of a dual copy of Z2. So you see, for every divisor, you can attach some kind of an integer vector in that lattice. And if you make that picture, so if you make that picture, you have a Z2, and then you have some kind of, 3 special vectors. And, okay, and then there's more. You can associate open subsets to some regions there, and so on, and you get a picture called a fan. But for our purposes, the most important thing will be this, the rays of the fan correspond to torus invariant divisors. That's what, and Arijit will also use this duality tomorrow to describe what he wants to. Okay? Now, I can tell you, well, let's see. So I want to tell you so basically you notice that in an X, there are such kinds of cones, sigma, and you can actually identify those sigmas with the torus fixed points. So in the complete case, you can do that. Each cone in the fan identifies with a torus fixed point. And now, okay, so, and of course, this torus fixed point lies in some affine toric variety. You can here delete this divisor, and you get a copy of C2. So that's right. So I have a bunch of, this is, X is union of some affine toric pieces called X sigma, and I have sigma n dimension, top dimensional cone, or a T fixed points. So you can identify them with like that. And okay, so these are affine toric variety. Okay, and on each one I have a section S sigma and a homomorphism rho sigma. So given a principal gamma equivariant principal bundle, I have, so given EG, for each sigma, we have an S sigma, okay, at least one S sigma, and an associated rho sigma from gamma to G, right? Now, actually, it's very hard to classify how many such sections you have, okay? So that's difficult. How many such, trivializations are there? That's really, we don't know the answer to that. But what we know is that the rho sigmas are easily classified because rho sigma corresponds to action of gamma on EG X sigma, say the fixed point, EG little x sigma. So this, if you know one of them, all others are just conjugates. Okay? So rho sigma is well defined. This is depends on a sigma, but are all conjugate in G. That's what we know. Okay. So that's the key part of the classification, one key part of the classification that, although you don't understand you don't have a good finite type classification of these S sigmas, you have a good classification of the rho sigmas. Now what we can do is we fix a point, x0, say, fix x0 in dense orbit. Actually, you can identify this x0 with the element 1, 1, 1 in C star to the n, the torus. Okay. Anyways, that's not so important, but it's kind of convenient thing to do. And now what you do is you fix your sections, say, and you look at S sigma x naught, the transitions exactly at that point, S tau x naught, and I have to be careful. I think this element of G I called P, well, okay, maybe it's hard to remember whether tau comes first or sigma, but let's just say. So then this P tau sigma is an element of G. And okay, if I change, okay, so if we change S sigma to, so this is entire collection, right? One for each of these fixed points, to S sigma dot G sigma, then what happens is that the rho sigmas will change to, I believe, G sigma inverse rho sigma G sigma, and the P tau sigmas will change to maybe one of these. Well, it's in there, but P tau sigma G tau, or G tau inverse G sigma, one of those. Okay. So you have this, and also notice that this P tau sigma behaves like a one cocycle, so that P tau sigma, P sigma delta, P delta tau is 1, so it's a one cocycle. G valued one cocycle. So I have this kind of data I get from such a bundle, and then this kind of data up to some equivalence relation classifies the principal bundles, gives you the isomorphism classes of principal bundles. So yeah, tau is like another fixed point or another affine piece. Okay. So yeah, so okay, so it defines what is called an admissible collection. So a collection of these rho sigmas, P tau sigmas is called, well, so here sigma tau are n-dimensional cones, or top-dimensional cones, or fixed points, whatever you think. So it's called admissible if, number one, okay, so, all right, there's this thing, so G sigma inverse P tau sigma G tau. Okay, maybe, I'm getting confused. So better, look. Okay, sorry, not this, but yeah. So rho tau t, rho sigma inverse T, T in the torus. So these are the, the equivariance forces you to get these transition functions. Okay? So you have the transition on the special fiber, and then the way the section spread, you have automatically. So now what we have is that this is extends so now this is well defined. This is a regular on the torus. It has to extend algebraically to the intersection of the two affine pieces, which is bigger than the torus, okay? So that's one condition. And the other conditions are kind of easy. So you have that, rho tau sigmas 1 cocycle, I guess, and you can put rho sigma is always 1. Okay. All right. So with these three conditions, we call this an admissible collection. Right. And now there is some equivalence relation on the admissible collection that if I change, I'm allowed to conjugate this rho sigmas, and as I showed you there, so I can conjugate the rho sigmas, and I can, like that, and I can conjugate this. So you look at admissible collections, and this defines equivalence relation, and you look at equivalence classes, and those equivalence classes gives you isomorphism classes of gamma equivariant principal bundles on the toric variety. And actually, what we can do is, if the group G is nilpotent, then we can actually get some formulas. So classically, there is a formula for line bundles. How many isomorphism classes are there? Now, if G is nilpotent of a certain type, we can actually calculate formulas. So I don't have time to write that. And just a few words about what Origis is going to do. So this is a classification up to isomorphism. So what he's going to talk about is classification up to equivalence of categories. That's a much stronger classification. And so that's what he's going to do tomorrow. Thank you. Oh, sorry. Actually, in all this, I forgot. I said analytic trivialization implies algebraic. Now, I didn't explain how one gets the analytic trivialization. This is done by something called an equivariant Oka-Grauer principle. Is due to Heinzner and Kuschebach. And that's a really difficult work.
Where did you condition on the factorial actually enter? Was that?
Okay. Yeah, so I wanted so I have a rational function and that extends, that has limits to the boundary. And I want to show that at every boundary point, it is regular. So I have to cancel out the factors that vanish. And that's where it enters.
So
you are assuming the point where it has like non-trivial isotropy, that is the full group torus.
Yeah, so the fixed point, this can be, yeah, that's a good question. So in this version, the one that I'm presenting, I'm assuming that the isotropy is the full torus. Now, if it is not, then we can easily deal with that. What we do is you can decompose the toric variety as a toric variety of smaller dimension with a smaller torus acting with full isotropy times another torus. And on the other torus, you can just extend this action by equivariance because the action will be free there. Thank you.